Okay, let's dive into this. Welcome back to today's explainer. Today, we're completely decoding the abstract architectures of the atom. We interact with matter literally every single second of our lives, but how often do we actually stop to think about the invisible scaffolding holding it all together? So we're zooming all the way in today to really understand chemical bonding and molecular structure. Here's the micro to macro blueprint we're going to follow to get you prepped for your exams. 1. The quest for stability. 2. Stealing versus sharing. 3. 3D molecular blueprints. 4. Quantum bonding theories. And finally, 5. Bonds in the real world. Let's get to it. Section 1. The quest for stability. Why atoms actually form bonds. I want you to think of atoms not just as static spheres, but as tiny, microscopic builders. And that brings us to, honestly, the most fundamental question we can ask in chemistry. Why do atoms form bonds in the first place? What's the core motivation driving an atom to interact with another atom instead of just existing completely on its own?
Well, the crucial takeaway here is that it all comes down to energy and stability. The ultimate goal for literally any atom is to achieve a lower energy state. Why? Because in our universe, lower energy equals higher stability. Atoms pull this off by striving to complete their outermost shell, getting that coveted octet of 8 electrons, or a duplet for the smaller elements. They're basically trying to mimic that highly stable, super unreactive configuration of the noble gases. So bonding, it's really just nature's way of finding the most relaxed, stable state possible.
All right, section 2, stealing versus sharing. We're talking ionic versus covalent bonds. Once an atom decides, hey, I need to achieve that stable state, it basically has 2 main economic strategies to get there. Over on the left, we've got the causal concept. This is essentially about outright stealing or transferring electrons. One atom gives up an electron, another snatches it up, and boom, you've got an ionic bond. Now on the right side, the Lewis concept is much more diplomatic. It's about cooperative sharing. Atoms actually share pairs of electrons to form covalent bonds, and you'll see this represented by those classic Lewis dot symbols drawn right around the atomic symbols. And this brilliantly illustrates exactly how that causal approach, the ionic bond, actually goes down in 3 distinct steps. First up, we have the formation of a positively charged cation. Think of when sodium loses an electron. Second, you get the formation of a negatively charged anion, like chlorine eagerly gaining that exact electron. And third, the massive electrostatic attraction between those oppositely charged ions just snaps them together. And there you go, that is the literal recipe for an ionic solid, like sodium chloride. But look, even when atoms decide to share electrons in a covalent bond, they don't always share fairly. And here is a massive pro tip for your exam prep: focus on the dipole moment. This formula right here, mu equals q times r, where q is the magnitude of the charge and r is the distance between them, this is exactly how we measure a molecule's polarity. It's the key to distinguishing polar molecules, where the electron pull is super uneven, like in hydrochloric acid, from nonpolar ones that have a net zero dipole moment, like carbon dioxide. The whole dynamic is totally dictated by electronegativity, especially when you've got highly attractive elements like fluorine in the mix. Moving on to section 3, the 3D molecular blueprints. Let's look at VSEPR and hybridization. So now we're zooming out from the mechanics of single bonds to look at the actual 3-dimensional architectures these atoms build when they get together. If you're taking notes right now, seriously screenshot this table. This is the beating heart of VSEPR theory, the valence shell electron pair repulsion theory. And the core concept here is beautifully simple. Electron pairs around a central atom absolutely despise each other. They actively repel one another and will arrange themselves in 3D space just to get as physically far apart as possible. Take a look at water down at the bottom there. You've got 2 bond pairs and 2 lone pairs. Those lone pairs literally push down on the bonds, which forces H2O into that iconic bent shape we all know. But if we really want to understand these shapes, we've got to talk about hybridization. See, it's not just about electrons pushing each other around. It's about atomic orbitals of similar energy quite literally intermixing to form brand new, perfectly equivalent hybrid orbitals. For example, if 1s and 3p orbitals mix together, you get sp3 hybridization, and that always dictates a tetrahedral geometry just like you see in methane. The final geometry is totally hardwired into how those original orbitals combine. Which brings us to section 4, quantum bonding theories. Time for VBT and MOT.
Now we're taking a step deeper into the advanced engineering happening right down in the quantum realm. Valence bond theory tells us that covalent bonds actually form through the physical overlap of atomic orbitals that contain unpaired electrons. But, spoiler alert, not all overlaps are created equal. A sigma bond is a direct head-on collision. It is highly effective and makes for a really strong bond. A pi bond, though, that's a sidewise parallel overlap. It's secondary, it's definitely weaker than a sigma bond, and here's the kicker. It only forms after a sigma bond is already in place. You see this happening all the time in double or triple bonds. And that takes us to our next major leap, molecular orbital theory, or MOT. MOT proposes that atomic orbitals actually combine mathematically to form entirely new molecular orbitals. And these belong to the whole molecule, not just the individual atoms anymore. When they combine constructively, they form bonding orbitals. This lowers the overall energy and stabilizes the molecule, which is great. But when they combine destructively, they form antibonding orbitals. These are higher in energy and actively destabilize the molecule. So it's basically this constant microscopic tug of war. So how do we actually know who's winning that tug of war? Well, we use the bond order formula. You take the number of bonding electrons, subtract the antibonding electrons, and divide the whole thing by 2. Honestly, guys, this is a huge focus area for your exams. Why? Because the bond order pretty much tells you everything you need to know. A higher bond order, that means a stronger bond, a shorter bond length, and a way greater bond energy needed to break it. And if the bond order calculates out to 0, the molecule simply cannot exist. It's totally unstable. Just take a look at this number right here, 3. This is the bond order for a nitrogen molecule, N2, and because it has such a massive bond order, a triple bond, it is incredibly stable, structurally rigid, and takes a huge amount of energy to break apart, especially when you compare it to a molecule with a bond order of just 1. All right, final section, Section 5, bonds in the real world. Let's look at some macroscopic properties. Okay, it's time to connect all these microscopic quantum blueprints to the macroscopic world that we actually touch and see every single day. Think about the metals you use all the time. All their properties? They come straight from metallic bonding. Just picture a sea of delocalized electrons. You've got these positive metal ions sitting perfectly in a structured grid, but they're completely swamped by freely moving shared electrons. Because these electrons aren't tied down to any single atom, they can carry heat and electricity almost instantly right across the material. It's also exactly why metals are so malleable. Those ions can just slide right past each other without shattering the whole structure. And finally, we absolutely have to talk about hydrogen bonding. Now, this isn't a full covalent or ionic bond, but it's an incredibly strong attraction between a hydrogen atom and a highly electronegative atom, specifically fluorine, oxygen, or nitrogen. You've got 2 main flavors here. There's intermolecular, which happens between different separate molecules. Think of water molecules sticking to each other. And then there's intramolecular, which actually occurs by folding within a single molecule itself. The real-world impacts of hydrogen bonding are absolutely massive. I mean, it's the whole reason water has such an unusually high boiling point, which literally keeps our oceans liquid. It's what allows alcohols to be soluble. It's even the exact molecular force holding the 2 strands of your own DNA together in that perfect double helix. And, kind of beautifully, intermolecular hydrogen bonding forms this rigid open lattice when water freezes. That's the exact reason why solid ice has a lower density than liquid water, allowing it to float right on top. So, from the desperate quest for atomic stability, to the precise geometric shapes of water, down to the actual molecular forces holding your DNA together, everything is bound by these hidden rules. It really makes you wonder, doesn't it? What other invisible architectures are silently shaping the universe around you right now? Keep observing, keep questioning, and I'll catch you in the next explainer.